Okay, hello everyone, welcome back. How has your week been so far? Okay, hello everyone, welcome back. How has your week been so far? Oh, God, okay. All right, so yeah, how's everyone doing? Good? Good, cool. So, yeah, so what we're going to do today is we're going to finish off the recursion lecture from Tuesday, and then we're going to move on to our next topic, which is going to be analysis of algorithms. Okay, so yeah, so this is where we stopped last time. We were looking at how list depend works and how you need to use the pattern of list next equals list depend list next, right? And I explained how if you have a recursive function that modifies a list, then you'll probably need to use this pattern, right? Because if the next node changes, then that function needs to return that information back to the current function, right? Okay, and then I also showed you an exercise. I added one more here. So there's one here which is return a copy of a linked list. And then there's the one which I showed you before, which is delete a value from a linked list. Right, so I'm not going to go through these now, but they'll be in next week's tutorial. So your tutor will be able to go through them. And there is starter code on the course website for these, so you can try them out yourself. And then, yeah, see if you can do it. So I got a question about if we can go through case 2 for the one where the rest of the list is empty. So this would be for list depend. So we could have a look at that. So case 2 is where the list is not empty. Is that what you meant? Yeah. Okay, so yeah. So let's go through this again. So remember that when we call a recursive function, right, we will assume that the function works, right? So in this case, when we call list depend, we're going to assume that the value gets added to the end of the list. Okay, and in case 2 here, the rest of the list is not empty, right? So it has at least one node. So what this recursive call is going to do, list depend, list next value, is it's going to add the new value to the end of the list, right? So we're assuming that the function works, and it adds 5 to the end of the list. Okay? And what else does list depend do? Well, list depend also returns back a pointer to the beginning of the updated list, right? So, well, since the rest of the list wasn't empty, the head of the rest of the list isn't going to change, right? So that means list depend is just going to return back a pointer to the same node that we gave it, right? So which is this node over here, okay? So that's the function call, right? So the function call is going to add 5 to the end of the list and return back a pointer to this node. Now, how about this part of the line, list next equals, right? Well, that's going to set list next, so the next pointer in this node, to whatever list depend returned, right? Which is a pointer to this node. Okay? And since this next pointer is already pointing to that node, this assignment statement here doesn't actually do anything, it doesn't change anything, but it shouldn't change anything, right? Because we're adding to the end of the list. Since we still have more nodes ahead of us, our next pointer shouldn't change, right? Should still point to the same node after we have finished everything. Okay? Yeah, so yeah, cool, no worries. Okay, yes, so for these exercises, I'll leave you to try them out yourself. And I'll put up solutions to these next week, right, on the lectures page. Okay, so there are just a few extra things that we wanted to talk about. So one of them is recursive helper functions, right? So sometimes when you're given a function and you're asked to solve the problem recursively, you can't recurse using that function that we gave you, right? And one of the reasons is that maybe the data structure uses a wrapper struct or something called a container struct, right? I'll show you an example of that in a bit. And another example, another reason is that the recursive function needs to take in some state, right? That needs to get passed down through the recursive calls. So for one, this is an example of a linked list that uses a wrapper struct, right? So in a typical linked list, we have nodes that contain values and next pointers, but often in this course, how we represent lists is we have a struct that contains a pointer to the first node, right, of the list, right? And there are many benefits to having a container struct like this. One benefit is that we can add extra information to this struct about the list, right? For example, what's something that we might want to include in this struct? Any ideas? Yeah?
The length of the list.
Yeah, the length of the list. Perfect. So we might want to store the length of the list inside that struct so that if we want to find the length of the list, then that's much more efficient, right? We can just return whatever is in the struct instead of going through the entire list and counting how many nodes there are. Okay, so yeah, here's how we would represent the data structure in the code, right? So we have the node struct here, and then we have the list struct, which contains a pointer to the first node. Yep, so the question in chat is, how would this be different from a regular struct? So they would both be structs, but they would contain different things, right? Or the fields would represent different things. Yeah, so this one is the node struct that contains the data and the next pointer, and this is just a struct that contains some metadata about the list, right? So we can't just use a regular struct to make it recursive. So if our linked list, so if we don't have a wrapper struct in our linked list, then we can use recursion, right? So we can recurse like we did here with list next, right? But in this case, if we do have a wrapper struct, and we're asked to implement this function where we take in a pointer to this wrapper struct instead of a node, then, well, we can't use recursion using this function, right? Because what do we recurse on? Right? When we recurse, what do we pass in to the function? What we really want is for the function to take in a node, right? So that when we recurse, we can pass in a pointer to the next node. Right, so the way to deal with this is to use a recursive helper function, right? So in addition to this function here, which takes in a list struct, we're going to have a helper function that takes in a node struct, and that does the recursion, right? So this function here works exactly the same as the list append function that we saw earlier, except it's getting called by this, the original function that takes in the list struct. Okay? Yeah. So our function takes in the wrapper struct, and then we create a helper function, a recursive helper function, that takes in a node, right? And we pass in a pointer to the first node in our original function. Okay, so the second reason why we might want a recursive helper function is we want to pass in extra information, such as state information. And there are algorithms called backtracking algorithms, which are recursive, where you would want to keep track of some information as you are traversing, through whatever it is that you're traversing, right? But here, I'm just going to show you a simple example. So we have a linked list, and we want to print out the list in a numbered form, right? So I want to print out 1 before the first number, then 2 before the second number, then 3 before the third number, and so on. Okay, so if we wanted to implement this recursively, think about how this would work, right? We would have to print out a 1, right, before the first number, but when we recurse, how do we make sure that the recursive call prints out a 2, right? Well, since the function only takes in a list, a node, right, it can't keep track of that information. So what do? Well, we create a recursive helper function, right? So what we do is we create a recursive helper function that takes in a number, right? And then that number is the number that we would want to print out before each list item, right? So in our recursive helper function, we check if the list is empty, right? If the list isn't empty, then we print out the list item, list value, with the number before it, right? And then when we recurse on the next node, but we pass in number plus 1. Right? That way, in the next recursive call, we print out number 2 instead of 1. Right? And then in the original function, we pass in a pointer. We pass in the pointer to the same node, and then we pass in the number 1, right? Because that's the first number we want to print. Okay. So there's one last point here about recursion versus iteration. So keep in mind that a lot of the problems that we solved in the lecture can also be done using loops, right? While loops. But the reason we're teaching recursion is to teach you a new way of thinking, right? A new way of solving problems, which is to solve problems in terms of subproblems. And we'll see a lot more examples of that in future topics. Okay, but yeah, how do recursive solutions compare to iterative solutions? So thing is, if you have a recursive solution and there is also a simple iterative solution, then generally simple in terms of efficiency, then generally the iterative solution will be faster, right? Or the recursive solution will be slower. And that's because every time we recurse, every time we call a function, we have to create a new stack frame, right? The program has to create a new stack frame for the function. That takes some time to set up. So it's going to be slower, right? And another consequence of recursive solutions is that they take more memory, right? Because of those stack frames, right? So, yeah. So every time we have a recursive call, it creates a new stack frame. Okay, so yeah, so that's the end of the topic. So does anyone have any questions about recursion before we move on? Okay, so if not, we'll move on to analysis. Okay, so yeah. So this topic is called analysis of algorithms. So what we're going to look at is how to analyze algorithms and determine their time complexity, right? Time complexity is how much time an algorithm takes to run as a function of its input size, right? So yeah, we'll go through a lot of examples of analyzing algorithms, and we'll go through how to analyze algorithms, different ways of analyzing algorithms, and so on. Right? And the reason we want to analyze algorithms, remember, is so that we can determine whether an algorithm is feasible or not. Right? If you've designed an algorithm and you want to know whether you should implement it or not so that you can use it, then you should analyze it first. And we can also use it to compare different algorithms. Right? right? Which algorithm is faster? Okay, so yeah, why do we care about efficiency, right? Well, efficiency is really important for many applications, right? Finance, so if you've heard of like high frequency trading, then the programs that run for these high frequency trading companies have to be really efficient. Robotics is also an important application, right? The robot's got to respond relatively fast. Games, right? You don't want your game to run at like 10 frames per second, right? So the game's got to be relatively optimized. And database systems, right? If you've got thousands of users accessing a database at the same time or making requests at the same time, which hit the database, then you want to make sure your database is efficient. Okay, and you want to be able to compare programs, right, which I already mentioned. So if you have two programs, how do you decide which one to use? And I already mentioned the last point as well, right? If you design an algorithm, how do you tell if it's going to be fast enough and if you should implement it? Okay, so for efficiency, how do we tell or how do we determine how fast the program is going to run? Well, there are a lot of factors in play here, right? First of all, there's the computer itself, right? So the operating system. There is the compiler, right? So some compilers are better than others and they'll simplify the code more. And that might result in fewer operations needing to be performed. There's hardware, right? So CPUs, GPUs, they're getting faster year on year. And caches. So caches are another thing that computers have that speed things up. Load on the machine. So if you've got more programs running on the computer at the same time, then the program is going to run slower, right? Because the computer's got to switch between each of them. Okay, but the most important thing, and as programmers, right, the thing that we have control over is the data structures and the algorithms that we use. Right, so as programmers, we don't really have control over, what compiler the user has on their computer, right? What hardware they're running on, and how many programs they're running on the computer, right? We have control over what algorithm we use and what data structure we use. Okay. Cool. So one important point is that the time that an algorithm takes to run typically depends on the input size, right? So usually the larger the input is, the longer the program is going to take, right? Because you can imagine that a program is probably going to have a loop in it, right? That's going to loop over the data, and the more data there is, the more time the loop takes to run, right? So yeah, so if your algorithm is efficient, then even for large inputs, it might run really quickly, right? And if your algorithm is really slow, really inefficient, then for large inputs, it's going to take a very long time. Okay, so when we're analyzing algorithms, there are different cases that we can consider, right? So there's best case, average case, and worst case. Right? So best case is for an input, right? What is the shortest amount of time that the algorithm could run, right? And this isn't very useful because usually best case performance only occurs for specific types of input. Right, so specific inputs or specific types of inputs, and it's definitely not indicative of how quickly the program is going to run on average. Right, so that's why there's average case performance. So with average case performance, well, we determine how efficient the algorithm is on average, right? And this is kind of the most realistic case, right? But it's difficult to analyze because, first of all, we need to make some assumptions about what inputs are going to be given to the program, right? And we might not have that data. But what we can really easily analyze is worst case performance, right? Because we can look at the program and we can see what path is the program, what path can the program take where it's going to take the longest amount of time, right? Okay, so can we turn up the mic volume? I can try. Okay, so I've turned it up a little bit, and I'll try to speak a bit louder as well, but remind me if I'm getting a bit low on volume again. Right, thanks. Okay, so now let's talk about time complexity. So time complexity is the amount of time that an algorithm takes to run, right, as a function of the input size. Right, so what I mean by function of the input size, I mean functions like these, right? So, for example, n squared, right, 6n, n log base 2n, 20 log base 2n. So these are all functions, right? And on the x-axis, we've got the input size. On the y-axis, we've got time. Notice that the functions are all increasing, right? Usually, an algorithm is not going to get faster if you make the input size bigger, right? So algorithm's always going to take longer. Okay, but soon we'll see that what really matters for analyzing an algorithm is not like the constants in front of the n, right? So the 6 here, we'll see, doesn't really matter for analyzing algorithms, right? And the 20, right? It's going to be these terms here, n squared, n log n, and so on. Okay, so how do we actually measure a program's time complexity, right? Algorithm's time complexity. So we can do it either empirically or theoretically, right? So empirically means we actually run the program and we measure how long it takes. And theoretically, it means we look at the algorithm. So we either have written the algorithm down in English or in pseudocode or with actual code, and we analyze that. Right, and we analyze it by counting the number of operations that it's going to perform, right? Usually in the worst case. Okay, so here's the problem that we're going to focus on for analysis, right? It's going to be searching, right? So given an array and a value, we're going to check whether the value exists, right? And if it exists, we're going to return the index where that value is. Okay, and if it doesn't exist, we're going to return -1. Right, so for example, if we search for the value 11 in this array, then we're going to return 2, right? Because 2 is the index that contains this value. Right, if we search for the number 7, then we're going to return -1 because there's no -1 in the array. Okay, so now let's analyze this empirically. So I've implemented the algorithm here, linear search. Right, so what does this program do? It reads in an array, right, over here, and then it calls the function linear search. Right, so linear search just does a for loop over the array. Okay, so what do you have to do to analyze a program empirically? Well, you've got to implement it first. Then you can run the program, right? And it's important to run the program with inputs of different size because otherwise you can't tell how fast the algorithm is going to grow, right? If you only have one data point, that's not going to tell you, is it going to grow in a straight line or is it going to grow in a curve or so on, right? So we run the program with inputs of different size and composition. So for composition, so for certain algorithms, you might want to analyze different types of input. For example, if you're analyzing a sorting algorithm, right, you might want to give the algorithm sorted inputs, so sorted array or reverse sorted array, or randomly sorted array, to tell how whether the algorithm performs differently for each of those inputs. Right, then you measure the running time, and then you plot the results, right, and see what trend you get, right, whether it's a linear trend, quadratic, or other. Okay, so for timing how long a program takes, there are also different ways we can do that. So firstly, there is a time command, right, that you can just run by typing time and then the program that you want to run. So here I'm just going to time the ls command. Right, and on different computers, the output displays differently, but ls is really fast, right? It just lists out the files in the directory, so it's taking 0.00 seconds here. Right, so there are different times here. User, system, the one we're going to focus on is user. Right, so 0.00 seconds. Okay, but the problem with using the time command is that it times the entire program, right? Sometimes we want to analyze an algorithm, right, but the program needs to do some setup before it runs the algorithm, or something else, right? So another way we can time an algorithm is to use the clock function, right? So we call the clock function to get the current processor time before we run the algorithm. Then we call it again to get the time at the end, and then we do some math to find out how many seconds the algorithm took. Okay, cool. So that's how we measure an algorithm empirically. And the really important point to mention is that since different machines are going to take different amounts of time, right? Computers from 20 years ago are going to be much slower than the computers today. So the absolute time isn't as important. What we're interested in is how quickly the time grows as the input size increases. Right? So if we double the input size, how much longer is the algorithm going to take? Right? It's going to take 2 times as long, 4 times as long, or even slower. Right, so there was a question about why this is being divided by clocks per second. It's because the time returned by clock here isn't in seconds. It's in processor time. And to get the number of seconds, we need to divide by clocks per second. Right, so this is, I guess, the amount of clock ticks that the processor does per second. Right. So there's also a question about, does time the entire program, not a specific function? So the way the clock function works is you call it before the algorithm and you call it again after the algorithm. So it's not timing the entire program, just a specific block of code that you can choose, right? Okay. Yes, so again, we were interested in the change in the amount of time the program takes as the input size increases, right? So here I have a question for you. So I've timed 2 algorithms, right? A blue algorithm and a red algorithm at this input size, so 14. The numbers here don't really matter. And I found that the blue algorithm takes this amount of time, so around 400 milliseconds, and the red algorithm takes this amount of time, about 200 milliseconds. So can you tell me which algorithm is more efficient? right? So who thinks the red algorithm is more efficient? Right, who thinks the blue algorithm? Cool, so the thing is we can't tell, right, with just a single input size, right? So for small input sizes, maybe the red algorithm is faster, right? But maybe for large input sizes, which is usually what we care about, right, large amounts of data, the blue algorithm actually runs faster, right? The shape of these graphs are completely different, right? One of these is a straight line, linear. The other one is a quadratic, like an n squared kind of curve. Right, so the really important thing is don't compare times, right? Compare growth rates. Yeah. Okay, so there was a question about which library is clock a part of. So it's in the time.h library. So it's hash included here. Okay, and there's also a question about, in this case, we are considering just one input size. So doesn't it mean that the exponential growth would be ideal? So it depends on the data that you're giving to the algorithm, right? If you know that the algorithm isn't going to be taking in that much data, right, then you can use this algorithm, right? But yeah, do you know what data your algorithm is going to take in, right? Is it going to be a large amount of data or a small amount of data? Yeah, so let's go back to linear search. Okay, so remember what this algorithm does. It finds the value in the given array, and if it finds it, it returns the index. Otherwise, it turns -1. Okay. Cool. So I've already done the timing beforehand, and these are some results that I got. Right. So remember, the computers are really fast. So even if you give it 1 million items, right, it's taking 0.002 seconds. Right. So that's why it's important to get more data and try larger input sizes so that you can actually see what the trend is. And if we put these results into a graph, we can see that the time taken grows linearly, right, in a straight line. Okay, so yeah, that means the worst case running time. So what we're timing here is we're timing the worst case, right? And the worst case of linear search is when the value doesn't exist in the array, right? When the algorithm has to go through the entire array and it doesn't find the value. So this is how long the algorithm takes in the worst case. And we can see that it grows linearly. Okay, so that's empirical analysis. And there are a bunch of limitations of empirical analysis, right? First of all, it requires you to implement the algorithm, right? And that can be tricky depending on the algorithm, right? If the algorithm is really complicated, then it might be really time-consuming to implement it. Yeah, another limitation is that you might have to try different types of input, right? Because depending on the algorithm, different input types might result in different time that the program might take, right? So for one type of input, the amount of time taken might grow linearly. For another type of input, the time taken might grow quadratically, so n squared. And we'll see that next week with sorting algorithms. But yeah, so the consequence of this is that you would have to time different types of input. right? And another limitation is that the results that you get depends on the machine that you're running the algorithm on, right? So, and it depends on not just the computer, but the load on the machine, for example, right? You have to make sure that when you time the algorithm multiple times, the environment is similar every time. Right. Okay, and if we have two algorithms and we want to compare them, then we need to make sure that we use the same environments, right? So the same inputs, same hardware, and so on. Okay, so that's empirical analysis and its limitations. So does anyone have any questions? Yeah?
What does clock per second mean?
Clocks per second.
Yeah, like week before.
Yeah, so clocks per second. So I don't have a definitive answer to this, but I'm assuming it's the amount of clock ticks in the processor.
Like, is it like something that you already know, or is it something that there's assigned like a number to?
This is, yeah, so this is a constant, should be provided by time.h.
Oh.
Yeah. Yeah, but yeah, so it's a built-in constant. Yeah, I didn't mention that before. Cool, so any other questions? Okay, so yeah, now we'll talk about theoretical analysis. Right, so we saw the limitations of empirical analysis. We have to implement the algorithm first, but what if we don't want to implement the algorithm? Well, we can still analyze our algorithm if we read the code or the pseudocode and we count how many operations the algorithm is going to perform. Right, so theoretical analysis uses a high-level description of the algorithm. Right, so you could use the pseudocode. Right, if you already have implemented the algorithm, then you can use the code, and it describes the running time as a function of the input size. Right. Cool. And the nice thing about it is that it's independent, the analysis is independent of any hardware. Right. Okay, so I already mentioned pseudocode a few times, but pseudocode is a language-independent description of an algorithm. Right, so it kind of abstracts away the details of the algorithm because different programming languages have slightly different ways of doing things, right? Like declaring a variable. Some programming languages require you to manage the memory. Some programming languages automatically manage the memory for you. So the pseudocode isn't going to contain these details. Right, so it's not going to contain variable declarations or allocating string memory. Okay, but it will use constructs that are common between most programming languages, like if statements and loops. Okay, so here is the linear search algorithm written as pseudocode. Right, so we have here, notice that when we declare the function, we're not declaring the return type or anything. We're just specifying the names of the arguments, right? And this isn't just the only way of writing pseudocode. There's no standard convention for writing pseudocode. This is just one that I decided to use because it's concise, right, and terse. So the input to our algorithm is an array of size n and a value, right? And the output is going to be the index of the value in the array if it exists, right? Or -1. Okay, and inside our algorithm, we have a for loop from 0 up to n-1. right? And if the index I contains the value, right, a bracket I equals value, then we return I. Right? Otherwise, we return -1 at the end. Okay, so that's the pseudocode. So when we're counting operations, right, there's this assumption that we're making, right, that every program has these primitive or basic operations like addition, subtraction, multiplication, array indexing that each take a constant amount of time, right? So they might not all take the same amount of time, right? Because multiplication would probably take longer than addition, right? But they will all take some small constant amount of time, right? And that's an important assumption that we make when analyzing algorithms, right? So that we can count them, right? And then we can use the total count of the number of operations to determine what the time complexity is. Okay, so these are some primitive operations: assignment, indexing, calling a function, returning from a function, evaluating an expression like addition, and incrementing or decrementing. Okay. Yeah, and I mentioned this already. Okay, so let's try and count primitive operations for this simple loop, right? So let's ignore the contents of the loop. Let's just focus on this one line, right? So how many primitive operations is this line going to perform? So let's think about it, right? How does a for loop work? So in a for loop, we have an assignment that runs once, right? So that's one primitive statement. And then we have a condition, right? I less than n, right? So when is this condition going to be checked? How many times? So what's the consensus? Who thought n minus 1? Who thought n? And who thought n plus 1? Yep, okay. So I think it's going to take n plus 1 times. The reason is because we check the condition. So first of all, this for loop is going to have n iterations, right? And it's going to check the condition after each iteration. So that's n times, but it's also going to check the condition once before the first iteration, right? So that's going to be n plus 1 times. And the I++ is going to run n times, right? So it runs at the end of each iteration. So there's a question about, wouldn't I less than or equal to n run n plus 1 times? So if this was a less than or equal to, then it would run n plus 2 times. Yeah, so the reason this condition here runs n plus 1 times is that the for loop will check the condition once before the first iteration, right? And if the condition is false, then it's not going to run the body of the for loop at all, right? It'll just go to the next thing. Okay, so yeah, this is what we found, right? So 1 plus n plus 1 plus n. So that's in total 2n plus 2, right? So now if we also add in, so this was the for loop for our linear search algorithm, right? So if we add in the other operations, so the if statement inside the for loop, right? This line here contains 2 operations, right? It contains an indexing operation and a condition, right? So you're checking a condition, equality. Right, so that is going to add 2n operations to our algorithm, right? Because this if statement is going to run n times, right, in the worst case. So that's 2 times n. And then if we include the return statement, that's going to be one more operation. So in total, we have 4n plus 3 operations. Okay? Cool. So, yeah, so linear search, that means it requires 4n plus 3 operations in the worst case, right? Now, if we assume that a primitive operation takes this amount of time, c, or at most this amount of time, then that means our linear search algorithm is going to take at most this amount of time, right? So c times 4n plus 3. Okay, and there was a question about why 2n. So this is 2n because this line here contains 2 operations, right? Indexing operation and a condition, so equality check, right? So we're checking if a bracket I is equal to value, that's one more operation. And we're multiplying by n because this if statement is going to run n times, right? Because it's inside of this for loop, okay? Cool, so where were we at? So we're at this line. Yeah, so the time taken by linear search is going to be at most c times 4n plus 3, where c is a constant. Okay, so what I think we'll do, since the next part has a number of slides, we'll take a quick break here. So we'll take a 5-minute break and we'll come back at 10 a.m. Okay. Okay, so let's resume. So during the break, I got some good questions about this slide here. So the first one was, why aren't we counting return I? So I forgot to mention this, but okay, so the reason why we don't count return I here is because we're analyzing the worst case of the algorithm, right? So in the worst case, what would happen is the algorithm isn't going to find the value and it's going to return -1 at the end. So it's not going to return I, so that's why we're not counting it. And another one was this loop here loops from 0 up to n-1. Right, so, and in the previous slide, we had the condition I less than n, right? So when we're looping from 0 up to n-1, in the pseudocode, this is how we would implement it in the code, right? We use the condition I less than n, so that when I becomes equal to n, this condition is false, right? And the loop no longer runs, right? Okay, so yeah, back to where we were. So linear search takes this amount of operations in the worst case, so 4n plus 3. So if we assume that primitive operations take this amount of time, C, or the slowest primitive operation takes this amount of time, then that means linear search is at most going to take this amount of time, right? C times 4n plus 3. Okay, so now I just want to remind you that we're interested in how the time taken by the algorithm changes, right? How it increases as the input size increases, right? And what this is called is the asymptotic behavior, right? How does the time change as the input size approaches, like infinity? Okay, so one point that we want to make for asymptotic analysis is that lower order terms don't affect the asymptotic behavior of the algorithm, right? Remember, what is the asymptotic behavior? It's how the running time changes as the input size increases, right? So what we're saying here is that how the running time changes as the input size increases isn't affected by lower order terms, right? So when we analyzed linear search, we got 4n plus 3, right, primitive operations. So 3 here is a lower order term, right? Because it's just a constant, and we also have 4 times n, which is a variable, right? So lower order terms don't affect the growth rate of the algorithm, the growth rate of the running time of the algorithm. So if the running time of an algorithm is 4n plus 100, with linear search we saw that it was 4n plus 3, but let's increase 3 up to 100. So if the running time is 4n plus 100, then since n is a variable, right, as n increases, this lower order term here, 100, becomes less and less significant, right? So it's going to have less and less of an impact on the running time. Okay, so when we're analyzing an algorithm, we ignore lower order terms. Okay. Cool, and another thing with asymptotic analysis is that it's not affected by constant factors, right? So here is just an example to show why. So with linear search, it was we had a 4 in front of the n. So what we're saying here is that the 4 doesn't affect the asymptotic behavior. Right, and here's an example to demonstrate why. So suppose we found that the running time of an algorithm is n squared, right? So this is the running time, Tn, and that's equal to n squared. Right, so when we double the input size, how much longer is the algorithm going to take? Right, so if we substitute 2n into this expression here, so we substitute 2n here for n, then we get 2n bracket squared, which is equal to 4n squared. And because n squared here is, because Tn here is equal to n squared, we can replace n squared with Tn, and we get 4Tn. Right, so what this means is that when we double the input size, right, the time taken by the algorithm quadruples, right, it takes 4 times longer. Okay? So now, let's suppose that the running time of the algorithm is not n squared, like here, but 10n squared. Right? So if we now try to see how much longer the algorithm would take if we double the input size again, and we go through the steps, so we try to simplify this. So t of 2n is equal to 10 times 2n squared, right? We're substituting 2n here for n. So 10 times 2n squared, that's equal to 10 times 4n squared if we expand the brackets. And if we switch the numbers around, that's equal to 4 times 10n squared. And remember that 10n squared is just tn, right? T of n. So we replace the 10n squared here with tn, and we get 4tn. Okay, so what this is saying is that when we double the input size, the time taken also quadruples, right? Regardless of the constant factor in front. Right, so whether we have a constant factor or not, whatever the constant factor is, when we double the input size, the time taken quadruples. So there's a question about what n means. So n means the input size. So yeah, we usually use n to represent input size. So for arrays, for example, that would be the size of the array. Okay. Yep, so hopefully I've answered that. But yeah, so just to summarize the two things that we just talked about, asymptotic behavior isn't affected by lower order terms, and it's also not affected by constant factors. Right? So that means we can really simplify our running time to a single expression, right, without any factors in front. Right, so for this expression here, Tn equals 100n plus 500. If we get rid of the lower order terms and constant factors, we get n. Right, for 5n squared plus 2n plus 3, if we get rid of the lower order terms and constant factors, we get n squared, right? Because 2n plus 3 are both lower order terms, and we get rid of the 5, the constant factor. Okay, and if we graph out these two, so if we graph out these two functions, right, 100n plus 500 and 5n squared plus 2n plus 3, we see that even though for smaller input sizes, the 5n squared algorithm is faster, right? For larger input sizes, the 100n algorithm is faster, right? So what this is saying is that the algorithm with the highest order term, right? So n squared here is the higher order term. It's always going to take longer for large inputs. Okay, and there's another question about, do we just take the higher order power of term and ignore the constants? Yes, and we also ignore the constant factors in front of the higher order term. Yeah, so for example, for 5n squared, we ignore the 5 as well. Okay, so when we get rid of lower order terms and constant factors, then what we end up with is the big O time complexity, right? So you've probably heard of big O, or seen it before, but it's what we use to classify the asymptotic behavior of an algorithm, right? And that's what we use to express time complexity in this course, right? So with linear search, after we got rid of the lower order terms and constant factors, we ended up with n, right? So we say that linear search is ON in the worst case. Right, and this gives us an easy way to compare algorithms, right? If we have an ON algorithm and we have an ON squared algorithm, we can say pretty confidently that the ON algorithm is going to run faster for inputs, for sufficiently large inputs. Okay. Actually, that is just what I said, so yeah. Right, if algorithm A has a time complexity of ON and algorithm B has a time complexity of ON squared, then yeah, for large enough inputs, algorithm A will be faster. Okay, so okay, so let me start over. So big O is actually a mathematical notation, right? And there's a kind of formal definition which I've given here. And there's a more informal definition which I'll tell you. So if we have two functions, f of n and g of n, right, we say that f of n is big O of g of n, right? If for sufficiently large n, fn is bounded above by some multiple of g of n, right? So this is a bit of a mouthful, but as an example, right, let me just start up a text file here. So with linear search, we saw that it had 4n plus 3 primitive operations, right? Okay, and we simplified, so primitive operations, 4n plus 3. And if we got rid of the lower order terms and constant factors, we ended up with big O of n, right? So removing lower order terms and constant factors, we get n, right? So okay, so we can say that linear search is big O of n, right? And because 4n plus 3, right, is big O of n. Sorry, that was probably very confusing. But what I'm saying is that 4n plus 3 is big O of n because it's bounded above by a multiple of n, right? So 4n plus 3, we know, for a large enough n, 4n plus 3 is going to be bounded above by 5n, right? It's going to be less than 5n, right, if n is large enough. So we can say that 4n plus 3 is big O of n. Okay. Cool. And here are some other notations for time complexity that you might see. if you take further courses like COMP2521, but in this course, we're only going to be using big O. Right, so f of n is big O of g of n if f of n is asymptotically less than or equal to g of n. Okay, so what does this mean? Right, so since we can ignore all lower order terms and constant factors, right, what we can do is instead of counting the number of operations, which might be difficult, right, because each line might have multiple constant factors, it can be really easy to miss constant factors, to miss operations, sorry. Instead of doing that, we can just count the number of line executions, right? Because each line will contain a constant number of operations, right? So if we count the number of line executions here of linear search, then we get n plus 1, right? Which is 2n plus 1 in the worst case. Okay, so that will also simplify to big O of n. Right, so if we get rid of the lower order terms and constant factors, we get n. Okay, so in summary, if we want to determine the worst case time complexity of an algorithm, first we count the number of line executions performed by the algorithm, right, in terms of n, the input size. Then we get rid of all the lower order terms and constant factors, and then that is the time complexity, right, in big O. Cool, so yeah, example is here. So if we count the number of line executions, get rid of the lower order terms and constant factors, and we get big O of n. Okay, so there's a question asking whether I can explain what we mean by line executions. Yep, so line executions is how many times each line runs. Right, so instead of counting like the operations on that line, we just bunch them all up and count that as one, right? One line execution. So this line runs n times, this line runs n times, and this line runs once. Okay, and so the time complexity of linear search is big O of n, right? But throughout this course, we'll see a lot of different time complexities, right? So we'll see big O of 1, right? So that's if the algorithm takes the same amount of time, regardless of how big the input is, right? So that's called constant time. There's logarithmic time complexity. So this is big O of log n. Right? And we'll have a look at an example of a big O of log n algorithm in just a bit. There's linear time complexity, so big O of n. There are lots of algorithms which are n log n, and we'll see some examples of that next week. And we look at sorting algorithms, and then there's quadratic, n squared, cubic, n cubed, exponential, which is 2 to the n, and there are even factorial time complexities, which is big O of n factorial, but that's for really inefficient algorithms. So a question in chat is asking, is the analysis of complexity pretty much asymptotic analysis? Yeah, in this course it is. Yeah, but analysis of complexity kind of is so it's both like empirical analysis, right? That's one way of analyzing complexity, but there's also theoretical analysis. So what we have been going through is the theoretical analysis part. Okay, and these are the functions that I just talked about, graphed here. So I think the website that I got this picture from is called Big O Cheat Sheet, something like that. And it shows you the time complexities of a bunch of common algorithms, like sorting algorithms. So you can check that out. Okay, so going back to linear search. So linear search is big O of n in the worst case. Right, so is there a way for us to do search any faster? Right, so imagine, let's imagine you're looking through a phone book, right? So I don't know if any of you have phone books still, but if you try to look through the phone book page by page for something, right, it's going to take a really long time, right? But what is a more efficient way of searching through the book? What can you take advantage of? Yeah, so the fact that it's sorted, right? So we have a more efficient algorithm that we can use if our array is sorted, okay? So, yeah, and that algorithm is called binary search. Why is it called binary search? So we'll see. But the idea behind it is we start in the middle of the array, right? So we start looking at index 3 here. If we have an array of size 7, we will look at index 3. And if the value that we're searching for is equal to the value at that index, then we found it, right? Easy. But if the value we're looking for is less than the middle value, then we look on the left-hand side of the array, right? So we repeat the process on the left-hand side of the array. If the value that we're looking for is greater than the middle value, then we look on the right-hand side of the array. Okay, so yeah, depending on what the middle value is, we either have found the value, always search the left half, always search the right half. Okay. And this is the code for binary search, right? So let's go through this. So we have an array and its size and the value that we're looking for. Okay, and what we do first is we initialize two indexes, right? So low, which is 0, and size, and high, which is size minus 1, right? So this is the index of the last element of the array. And what we're going to do inside of our while loop, so our condition for the while loop is while low is less than high, right? So low and high essentially indicate what part of the array we are searching, right? So initially it is the entire array from 0 to size minus 1. And this condition is just checking if that window, so while that window is not empty, right, while low is less than or equal to high, we're going to keep searching. Okay, so inside of our while loop, we're going to calculate the middle index of our array. Right, so that's going to be low, or the middle index of the part of the array that we're searching. Sorry, so low plus high divided by 2. And we're going to check, we're going to access that index, and we're going to update high or low depending on what that value is. Right, so if the value we're searching for is less than the middle value, then we update high, right, so that it's equal to mid minus 1, so that now we're searching the left part of the array. Right, but if the value we're searching for is greater than the middle value, then we update low to mid plus 1, so that we're searching the right half of the array. Okay, and if the value isn't less than the middle value or greater than, then that means it has to be equal to. So if we found the value, we return mid. Okay, and finally, if we've halved the array enough times that we don't have any more elements to search through, then we return -1. Okay, because that means the element doesn't exist. Okay, so here is an example of binary search. So suppose we're searching for 6 in this array. Right, so first of all, low is going to be 0, high is going to be 5, and the midpoint is going to be 0 plus 5 divided by 2, right? So that's 5 divided by 2, which is 2. So that means we check this index, right? It's 5. Since 6 is greater than 5, what do? Well, we update low to be equal to mid plus 1, right? So we set low here to be equal to 3, so that now we're searching this right part of the array. Okay, what do we do next? So again, we calculate the midpoints, which is now going to be 3 plus 5 divided by 2, right? That's going to be 4. So we check the value at this index, right? Since 6 is less than 8, right? The value we're looking for is now less than the middle value. We update high, so that it's equal to mid -1, right? So now we update high to mid -1, which is 3. Okay, so now low equals to high, right? So that means when we calculate the midpoint, it's also going to be the same. So the value at this index is 6, and that's the value that we're looking for. All right, so we return mid. So we return 3. Okay, so here is another example of an unsuccessful search. So suppose we're searching for 7 in this array, right? So the middle value here is 5, so that means since 7 is greater than the middle value, we're going to update low to 3, to mid plus 1, which is 3. And now 7 is less than the middle value, which is 8, so we update high to mid -1, which is 3. And now 7 is greater than the middle value here, right? So that means we're going to update low to mid +1, right? And now low is greater than high, right? So that means this condition is false. Right? So that means the while loop stops and we return -1. Okay, so let's analyze binary search now. Right, so what's the time complexity? So in the best case, so remember we're focusing on worst case here, but in the best case, right, we find the item right away, right, when we check the middle element the first time. Right, so that means in the best case, the algorithm is O1, right? So one iteration. But in the worst case, how many iterations is the algorithm going to take? So remember that binary search is constantly dividing the array by 2, right? Each iteration. So the question is, how many times can we divide by 2 until we end up with an empty array, right? Or an array with one element. So that's equal to log base 2n. Right, so to explain that further, Right, so suppose we start off with an array of size n, right? And we want to figure out how many times we need to divide it by 2 before we end up with 1, right? Suppose. So we want to divide n by 2. So if we divide it once, then that's the expression there, that's the fraction. If we divide it twice, then the denominator is now 2 times 2. But what we're trying to find is the number of times we need to divide by 2 until we get 1, right? So here we're trying to solve for I, okay? So we want to keep dividing by 2 until we get 1, and we're trying to find out how many times we need to divide it by 2, right? So now we can multiply both sides by 2 to the power of I, right? So now we get n equals 2 to the power of I, right? And remember that log is kind of the opposite of exponentiation, right? Logarithms are kind of the opposite of exponentiation. So that means I is equal to log base 2n, right? Okay, so that's where we get the log base 2n from. Okay, that's the number of times we have to search or divide the array by 2 until we have nothing left. Okay, so log base 2n iterations. And that means binary search is bigger of log base 2n, right? Or we can actually get rid of the base and just write log n. Okay, so that's the question, right? So why can we ignore the base here? So the reason we can just ignore the base and just write log n is because if we have two different, so we have two logs with different bases, right? And they're both constants, so suppose log base 2n, log base 3n, right? It turns out that these two expressions are always within a constant multiple of each other, right? So I'm just going to jump to the next slide here to show you. Right, so if we have log base 2x here, so we have a graph of log base 2x, we have a graph of log base 5x. These two graphs are always a constant multiple of each other, right? And remember from theoretical analysis before that constant factors don't affect the growth rates, okay? Or constant factors don't affect the asymptotic behavior. So we can just ignore the base. But there's a more rigorous explanation here. Right? We can always change the base of a log by multiplying by a constant factor, which is kind of another way of saying what I just said. Okay. Cool, so that was binary search. So does anyone have any questions about that? About binary search? Okay, so yeah, what we're gonna look at now is what happens if we have multiple variables in our algorithm, right? Or in our time complexity, right? Because what if our algorithm takes multiple inputs, right? Maybe it takes one array, maybe it takes two arrays, and these arrays might be different sizes, right? So what we do is we give each of them a separate variable, right? We don't want to use n twice because that implies that the arrays are the same size, so we use n and m, okay? So here are some example time complexities with two variables. right? You can combine them in different ways. So you can have big O of n plus m. You can have big O of n times m. You can have big O of the maximum of n and m, big O of the minimum of n and m. You can also have n log m, or n log m plus m log n. All depends on the algorithm, right? So here's an example of an algorithm with multiple inputs. Right, so given two arrays, where each array contains no repeats, find the number of elements in common. Okay, so we have two arrays. Each of them doesn't contain any repeats, but we're going to find how many elements they have in common. Okay, so here is an algorithm that we can use to solve that. So first we have a for loop that loops through the first array, right? So it loops from 0 up to n minus 1. We have an inner loop that loops from 0 up to m minus 1, right? So what we're pretty much doing is for every combination of indexes of the two arrays, we're just going to check if the elements at those indexes are equal. Right, so if AI equals BJ, then we increment this counter. Right? We increment num common, and then we return num common at the end. Right, so the time complexity of this algorithm is big O of n times m, right? Because this outer loop here runs n times, right? The inner loop, right, for every iteration of the outer loop, the inner loop runs m times, right? So that means in total, the inner loop runs n times m times. And then this if statement, since it's inside the inner loop, it's also going to run nm times. And so is this line here. Okay, cool. So that's the end of the lecture. But we do have some stuff in the appendix which we can go through since we have time. So what I'll do is I'll actually go through some of my own examples first. Right, so what we saw earlier is that if we have an algorithm which is big O of n squared, right, and double the input size, then the algorithm is going to take 4 times as long, right? Okay, so here's my question to you. So if let's say we don't double the input size, but we triple the input size, right? So how much longer is the algorithm going to take? Yeah, so I'm hearing 9 times, which is right? So the algorithm is going to take 9 times as long. Yeah, and the simple explanation for that is because we're tripling the input size by 3, and the time complexity is n squared, right? So if we square 3, we get 9. Right? 3 squared equals 9. But you can also figure this out by going through what we did in one of the slides. Right? Suppose that the algorithm takes n squared time for an input size of n. Right? If we triple the input size now, so t of 3n, right, that's going to be equal to 3n squared, which is equal to 9 times n squared, which is equal to 9 times tn. Okay, so it's going to take 9 times as long. Okay, now let's look at another example. So suppose now we have an ON cubed algorithm. Okay, so if we double the input size, how much longer is the algorithm going to take? How much longer? Yep, so I heard 8. So yeah, so the algorithm does take 8 times as long. Okay. Cool, what happens if I triple the input size? Yep, 27 times as long. Yeah. Cool. So, yeah, and that's because 3 cubed is 27. Okay, so that's good. Now, let's suppose I'm running binary search on an array, right? So I'm running binary search. Remember, binary search is bigger of log base 2n, right? But we kind of dropped the 2 and we just wrote it as log n. Right, so I'm just making up numbers in my head now, but suppose that for an array of size 100,000, or let's actually increase that, so 1 million, binary search takes, let's suppose that it takes 5 milliseconds, right, in the worst case. So now, if I double the input size to 2 million, how long is binary search going to take? Actually, I'm not sure if this can be answered. I'm not sure if there's enough information here, but okay, let me add some information. Let's suppose for 500,000 elements, it takes 4 milliseconds, right? So, okay, how much time is it going to take for 2 million now? Seven, so it would be 6 milliseconds, right? Because the time complexity is log base 2n, right? So remember that every time you double the input size, binary search only performs one more iteration, right, than before. So if going from 500,000 to 1 million, that's one additional iteration, it takes 1 more millisecond. And if we double the input size again, it's going to take 1 more millisecond again. Okay, so now let's look at this exercise. So if we have a quadratic algorithm, bigger of n squared, and for an array or a data set of 1,000 items, it takes 1.2 seconds. So let me write that information down here. So we have O(n) squared algorithm, and for 1,000 items, it takes 1.2 seconds. All right, the question is, how long for 2,000 items? So how long? Yep, so times 4, which is 4.8. Yeah, because it's going to take 4 times as long because we doubled the input size. Okay, let's look at 10,000. So how long is it going to take for 10,000? 12 seconds. Are you sure? Yeah, I think it's going to be 120 seconds, right? Because if we increase the input 10 times, tenfold, then it's going to take 100 times as long, right? 120 seconds. Okay, let's look at this one. 100,000. So 100,000. How long is this going to take? How many seconds? Yeah, 12,000 seconds. Yeah, so this is getting, so this would be how many minutes exactly? So if you divide this by 60 seconds, it would be 200 minutes, I think. Okay, and then the last one is, okay, 1 million, but okay, we don't have to do this, but it'll take 20,000 minutes, right? Because it's, again, 100 times as long as it took for 100,000. Okay. Cool. So, yeah, these are the answers. So now let's look at, since we have 5 minutes left, we'll look at some more analysis examples. Right, so here is our algorithm. Right, it just has 3 nested loops. So what would be the time complexity of this? Yeah, so it'd be n cubed, right? Yeah, so one shortcut that sometimes works, but not always, is that if you have a loop, right, that kind of multiplies by what's inside the loop, right? So this loop, so since we have 3 nested loops, we get n times n times n, which is n cubed. Just be careful because you've still gotta like look carefully to see what the loop is doing. Okay. Okay, how about this one? So here we have a outer loop that loops from 1 to n, and we have an inner loop that loops from 1 to I, where I is the variable used by the outer loop. So what do you think the time complexity is going to be? Anyone have any ideas? Yeah, so I heard n squared. So n squared is right. And that's even though the inner loop doesn't loop from 1 to n, it loops from 1 to I. And the reason is that if we count how many times the inner loop runs, right, let's try to do this for each value of I here. So when I is 1, the inner loop runs once, right? Because it goes from 1 to 1. If the value of I is 2, the inner loop runs 2 times, right? Then when I is 3, the inner loop is going to run 3 times. So if we count all this up, when I is equal to n, right, the inner loop is going to run n times. So the last value in this sequence is n, and if we add all of this up, this is an arithmetic sum, right, that you might have seen from math, right? This is equal to n times n plus 1 on 2, right? And that simplifies to big O of n squared. Okay? Let's look at this one. So here we have a loop where we're multiplying I by 2 every iteration. So what's the time complexity of this loop? What was it? Sorry? Can't hear you. What do people think? So we have an answer in the chat. Yes, so it would be log n, yeah. Yep, so it's log n. Cool. And then finally, here is a kind of tricky one where, okay, we have int I equals 1, p less than or equals to n, and I plus plus. Yeah, what do you think? So this one is pretty tricky, and it turns out it is bigger of square root of n. Yeah. Yeah. Although I'll go back and explain the previous one. So I didn't explain this one. So the reason this one is bigger of log n is because we're doubling the value of I every iteration, right? So if you think back to binary search, what we were doing was we were dividing by 2 every iteration, and the number of iterations it took was log n, right? But here we're kind of doing the opposite. We're just doubling the value of I every iteration. So the number of iterations it's going to take is also log base 2n, right, which simplifies the log n. Okay, but yeah, the last example is a tricky one, and it's square root of n. But yeah, since we are at 10:55, I can explain this next week. Right? All right, so yeah, have a good rest of your week, and I'll see you next Tuesday.